So, so welcome to the fifth week of the facilitation of the course. We are moving gradually to the end of the class. So this week, which is the fifth week of the class, we shall be looking at analytical functions. And in analytical function, we try to see what are they and how to solve problems using those concepts and all these things. So that is what we are going to be considered this week. So I sent to you last week the PDF of this lecture note. I believe everybody has his or her own now. So the analytical function, we start with introduction. So we said a function f of z is analytic at a point z0 if its derivative f prime of z exists not only at z0 but at every point z in the neighborhood of z0. One, one can show that f of z is analytic the, using the partial derivative of u and v of all others exist and continuous function of s and y. What we are trying to say is that if you have a function u and v with respect to x and y as variable, we can use this to check if a function is analytic or not. But how do we do it? Let's say, for example, now we can take the second derivative of u with respect to x, which is also equal to taking the second derivative of v with respect to the x and the y. So in this case, we have taken the derivative with respect to x1 and also to y. But in this case, the two derivatives with respect to x twice. So which is also equal to taking derivative with respect to y and this. And also, this can be expressed as d dy of dv dx. So which is same thing as negative d du d dy dy, and which is same thing as negative du square dy square, which means that these two things, this one here and this one, by the time you combine them, is more equal to 0. If this exists, then you say the function is analytic. So thus, if you have u of x and v of x that satisfy Laplace equation, because this is more or less like a Laplace equation, this equation is more like a Laplace equation. So now, we now look at this concept in details now, that analytical function is an infinitely differential function such that the Taylor series at any point x in its domain, that is when you have this, converge to f of x for x in the neighborhood of x naught. The set of all real analytic functions on a given set D is often denoted by this. So a function f defined on some of the subset of the real line is said to be real analytic at a point S if there is a neighborhood of d of x of which fx is real analytic. The basic idea between these are, if you take the derivative of the function and you substitute for the value of x in the function, you must get the value. Once you have the value, then the function is said to be analytic. Now, there are rules or theorems that guide this behavior. One of them says that if the derivative of f of z exists at a point z, then the partial derivative of u and v exists at that point and obey the following conditions. One, if you take the u dx, it must equal to the v dy, and also the u dy must equal to minus the v dz. These above equations are called Cauchy-Riemann equation, which was what we omitted last week in our discussion. So this is what they call Cauchy-Riemann equation. So let u and v be real and single value function of x and y are called, which together with their partial derivative of the first order are continuous at a point. If those partial derivatives satisfy the Cauchy-Riemann condition at that point, then the derivative of x exists at that point. So let's look at Cauchy-Riemann equation now. A necessary condition that w is equal to f of z, which is this, we discussed this last week. The analytic in region R is that u and v satisfy Cauchy-Riemann equation. That is, if you take the derivative of u with respect to s and you take the derivative of v with respect to y, when you equate them, they must be the same thing. If you take the derivative of u with respect to y and take the derivative of v with respect to x, so if you equate them, it may be the negative of this that will give you this. So also we have this. This is where we started from. Now let's look at example now. This example says, show that f of z, which is a set defined by this, is analytic in Z, and that dEz dz is equals to Ez. Now, we know that Z here is a complex number which can be written in this form. So Z is equal to x plus IY. So by definition, f of Z, where you see Z in this expression, now you replace it with this, then we have this. So if you use the law of logarithm on this now, because we have positive here, it will be multiplication, it will be E of S dot E of Y. So this means that this one, E of S, will stand like this, and we know that E exponential high Y, we can write it in a trig function in this form. You know this, I discussed this with you. So now, by the time you look at this and you open the bracket here, you will see that ES cos Y will be our U, and ES I sin Y will be our V. So the U of SY is this, and V of SY is now equals to this. So now, to now show that this satisfies Cauchy-Riemann equation, what we do is that we take the derivative of U with respect to X, which is this, the U, the S of this function now. When you take derivative of, this is only X there, this one is a constant, it will remain constant. If you take derivative of exponential, it should still be an exponential, this. Now, if you take it related to Y now, so this E of x is a constant, it remain there. Then when you take derivative of cos, it will give you negative sign, which is this. So we have the U dy. Do the same thing for V. This is a constant. Take derivative, the V ds will give you this. Then the V dy. When you take derivative of sine, it will give you cos. We have this. So now we now have all the four terms: the U ds, the U dy, the V ds, the V dy. Excuse me. Now, if you now use this expression to check if this thing satisfies Cauchy-Riemann equation, we are told that if you have derivative of this and this, if they are equal, they obey Cauchy-Riemann equation. Now, our du, the s, which is this, then the v dy, which is this. We now see that this and this are equal. The u dy, which is minus e sine this, then the v ds, which is this. By the time you put the negative, you see that they satisfy this condition. Hence, f of z is equal to this analytic. So to now show that f of z this is equal to this, it's just a matter of substituting and taking derivative. Take derivative of f of z. This is f with respect to z now. By the time you do that, you have the u dx plus this, which is equal to this and this. And by the time you express this and expand and use sign identity related to trig function, you have this back, which give you this. That shows that that function is same thing as this. Any question on that? Any question? Question?
Good afternoon. Good evening, sir.
Good evening. How are you?
Very fine, sir.
Okay.
The Cauchy-Riemann, is that the only example?
You said what?
Is that the only example? Like, I'm just coming, so I don't know if you've done another example.
Okay, no, this is just the only example we have just started treating. One thing you should know as regards to Cauchy-Riemann equation is that there are four things: the u dx, the u dy, the v ds, the v dy, which must satisfy this condition. Once you have them, they must satisfy this condition that the u ds must equal to the v dy, and the u dy must equal to minus the v ds. This is the condition. If all these four times, by the time you put them into the expression like this and they satisfy the condition, then they obey Cauchy-Riemann equation. Is that taken?
Yes, sir. But I don't know if there could be another example.
Well, I have just one example here.
Okay.
Yeah. Let's check if you have examples in the TMT. Oh, there's no other example there, just only one. Well, it's a straightforward function. Anyway, what you can do is that if you have access to engineering mathematics, I get me now. Engineering physics textbook. You will see a lot of examples there which you can use. Just follow the procedure. Is that taken?
Yes, yes, sir. Okay.
So any other question?
No. Okay. So that point, I think I'm just trying to like, so from that point, so u of xy equals to ex cos y, and v of xy equals to ex sine y.
Yes,
To be able to, that is the first one for du. You have to differentiate with respect to x,
exactly.
and then for v with respect to x for the
Yes.
other one. Okay, so
Very
like
cool.
first you separate it first as v and u
Exactly.
before
You
you start
separate them into
differentiating.
different terms as the
Okay.
real function and the imaginary function.
Okay, so like it has to satisfy the definition of Cauchy-Riemann by using the like u of x equal to v of x and u of y equals to minus v of
Minus d, exactly.
x.
That is the rule. And that's the procedure. Once you
Okay,
satisfy that, it obeys Cauchy-Riemann equation and it's analytic.
okay. So all Cauchy-Riemann are analytic.
Yes.
That means they are differentiable everywhere of f
They
of
are
z.
differentiable everywhere, especially when you have an x value. All the value within the neighborhood of the x value must satisfy that condition.
Okay. Okay. What of the y value?
The y, both of them are the dependable variable in this equation. So automatically, if it is y also, if you have the value for x naught and y naught, those values must satisfy this condition. Once they do, they obey Cauchy-Riemann equations.
Okay. Okay.
You know, if you look
Okay.
at this expression now, there are two things there, x and y. These are the two dependable variables there.
Okay.
So you can have
Yeah.
x naught and y naught as initial value.
Yeah.
Because if you know the
Yeah.
value of x naught and y now, you can determine what z is, isn't it?
Yes. Yes.
That is the implication.
Okay. 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 I'll check other examples there.
Okay, just try, check other example, then you see that it's a first is a straightforward functions and all these things that which is easy to understand and to deal with. So another question, because this week our class is very short, because the next thing we are going to be discussing is complex integral, which I will not start
I want
today.
to ask a question though.
You have a question? Okay, go ahead.
Okay. Like, can a function be differentiable at a point maybe z without it being analytic? No, right? It should be no, right?
Can a function be differentiable or analytic?
That is like without being analytic. Is it possible?
Yeah, it's possible. If the function is not if you take the derivative of the function, and for example now, if you have a function in which you take the derivative and you get an exact value, you know you have to take the function twice. You have to take derivative twice.
Okay.
So if you take the first derivative and you have an exact value, so if you take the second derivative, it gives you zero. Because a constant is not differentiable.
Yeah.
So automatically the function is not analytic.
Mm.
Did you get that there?
Well, but you notice that analytic function is about being differentiable. So why must they do it twice when it's
Okay,
the
now
first one is differentiable?
let's come here. See the definition of analytic function. They said a function is analytic at a point z if derivative of f prime z exists not only at z naught. You know the
Okay.
first one you do is at z naught.
Okay.
But by the time you take the second one, if it is not, then it's not analytic.
Okay. Okay. Okay.
This is second derivative, not first derivative.
Yeah.
Did you get the idea now? So if at first derivative
Yeah.
satisfy the condition, fine. But when you move to the second derivative and it doesn't satisfy, then it's not analytic. Did you get the idea
Okay.
now?
Okay. Yeah. 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 Okay. Okay. I understand it, yeah.
Okay. Another question?
One of the exercise assignments you gave us. Okay, the exercise you gave us last time. I've done them, but like I somehow need like your own solution.
Okay, which one and which one? You've tried
The
which
last year, on polar form
Let's go there together.
variable z bar.
Okay, this one. Are you talking of this?
Yeah, this one, yeah.
Okay. So what are your results?
Yes. Okay, so for the first one,
Okay.
I got a funny result. I kind of like, there was a fraction before my result, so it was something like 1/4.
Okay. Now, this is
So
what you do
3
for me.
minus
I think that is John Abi.
John Daniels, yes, sir.
John Daniel. What you do is that send your result
Yes,
to me
sir.
by mail.
Okay.
So I will look at it, then I will comment on it.
Okay, because I was thinking that normally used to have like the solved solution already. So
Yes, I do, but
thinking,
for this one, I've not solved all these ones myself.
okay. The only one I could not do though was cause the entire function.
Okay, this one, Abi. Are you referring to this?
Yes, sir.
Well, this is straightforward now.
Sir?
Okay, this is what I will do. I will try this weekend to solve it, and I will post to you guys.
Okay.
Okay, I will solve it this weekend and I will post to you guys.
Okay, sir.
Easy and straightforward. I will solve it this weekend and I will post to you. Another question?
Hello, sir. Somebody's mic is disturbing. I don't know.
Who is the person? I think that should be Victor or who?
Victor Chukuka.
Yes.
Who is Victor?
Yes, sir. Good afternoon.
Mike. Okay. Okay.
Okay, sir. So you say you will send it to us, right?
Yes, I will solve it this weekend and I will send it to you by email.
Okay. So the next one is residue, right?
Yes, the next the next thing we are going to discuss next week is complex integral.
Okay.
I don't want to model it up with this lecture today, so let's do it next week.
Okay.
It's just 1 week lecture. Then after that, we move to residual theorem. We're almost done anyway.
Although I noticed that some of the past questions contain things that are not in the textbook.
Okay. Do you have because I don't have access to some of the questions anyway.
Yes, I have access to like one question.
Send to me by email.
Okay, sir, I will.
Send it to me by email and let me look at some of the questions. Then I actually guide you. The point there is that
okay, sir.
I'm not the one that will set the questions. Mine just to put you through what they sent to me.
Are you serious?
Yes. I'm not the one setting the questions, but this is the instruction. This is the material sent to me to use to teach you. So I'll just teach it and I'll give to you. You go and meet it in exam. But if you have access to past questions, send to me. Let me see how the question looks like. Then I can actually guide you properly.
Okay, I'll look for them. I'll send them to you today, sir.
Okay, no problem. Thank you very much. So any other questions? So if there is no more questions, I think we have to stop the class for today. Then we meet next week.